Hello everyone, welcome to this video. I'm Jérémie Rodon and today I will speak with you about sovereign keys. So sovereign keys has been open sourced recently, so you can find it on GitHub right now. Probably you find this video from GitHub, so you know. And when you go over the README, it can be quite overwhelming. Okay, it's 1,500 lines and can be quite long. So today I don't want to go over all the README, but I want to first maybe take 15 minutes to explain the key points of the architecture. It will help us understand what we will do afterward. And afterward, I will go over the getting started with you. And my goal is to do it from scratch to scratch in about 2 hours. Okay, so I will start from nothing, show you how it's done, and end up with nothing after destroying everything. So yeah, that will be basically the goal today. So first, maybe a little architecture. So sovereign keys, it's an encryption system for AWS EC2 instances, and it's using external customer-owned hardware security modules as a backend for all the cryptographic operations and for protecting secrets. So the goal is to so that you can gain some additional guarantees about your ability to protect your data. And if we go over quickly how it's done, we can first comment this schema. So this schema is showing the functional design, the idea behind sovereign keys. So the idea is you have an EC2 instance, and this instance have a data EBS volume, so an additional volume data. It can be the instance store also, work with like a charm. And the idea is we use, instead of using KMS, which is on this schema only for reference to highlight the difference, instead of using KMS, or in addition, we will use BitLocker or LUKS. So BitLocker is the full disk encryption of the Windows operating system, and LUKS is quite the same thing for Linux operating systems. So LUKS is Linux Unified Key Setup, and it's actually a wrapper around device mapper crypt, so DM-crypt, maybe you know that. And those total disk encryption softwares are running inside the operating system, so it's at its right place in this schema. And to work, it has to get a key, okay, to encrypt and decrypt data on the fly. You can see that the OS will see the data in clear. Nothing will change for applications, for example. But when it comes to really storing the data, it will be stored encrypted. And the encryption decryption work is performed by LUKS or BitLocker, depending on the operating system you use. And it needs a key. And if you already set up those things at home, maybe you used your TPM, but in the cloud environment, it's not that easy to use a TPM. So instead, what we do is we use a passphrase, which is just another way to say a secret. And this secret will be provided by sovereign keys. So the goal is that ultimately sovereign keys protect the data, and ultimately it's the hardware security modules behind sovereign keys, so your own security modules, that will protect your data, because only those modules will be able to provide the secrets, which in turn will be mandatory to decrypt the data volume. So that's the idea. On a technical standpoint, what we will do today is deploy this infrastructure. So we will have a demo account, AWS account, that is, and we will have two VPCs, a dummy customer VPC, so a VPC that will simulate a customer. Customer is from the sovereign key standpoint, so if you are deploying sovereign keys in your company, it can be a BU, an application, a project, whatever. And you will have also a sovereign keys VPC, and the sovereign keys VPC will host the API. As you can see, the customer instance is not communicating directly with the sovereign keys instances. Instead, it's going through a private API gateway. So this is to make life easier when it comes to throttling, DDoS prevention. We thought it would be we would be better off not exposing directly sovereign keys instances to the customer instances. This private API gateway is also responsible for authentication. We will come back to that in a few minutes. When a request is handled by sovereign keys instances will be able to organize everything. So get information in this table. We will see what it is in this table. Retrieve the master secrets that will allow us to protect the instances secrets. So there is a hierarchy, key hierarchy that we will describe later. Sovereign keys will push logs in buckets. So there is a central sovereign keys bucket for logs. And optionally, there can also, in addition, we can have a customer log buckets. Again, customer is a BU, application, whatever. And of course, sovereign keys is performing its job by communicating, doing magic with an hardware security module cluster. And it's kind of floating outside of the diagram because we don't want to do any hypothesis about what it is. But today for our video, it will be a CloudHSM cluster because that's what I'm sure you will all have underhand because it's an AWS service. So the real architecture would look more like that. So you would have an AWS account dedicated to sovereign keys with the sovereign key VPC, the private API gateway, and everything really owned by the central system. And you would have multiple customer VPCs, multiple customer accounts, and you can see there is an IAM role going on, allowing the authentication to be performed cross accounts. But essentially, it's the same thing. You can read the cryptographic security on your own. I will just highlight the key points. So the key hierarchy. So the key hierarchy has 3 levels. And those 3 levels are the domain key, which is the top level. So the domain key ultimately protects everything. It never leaves the HSMs. And it protects the customer master keys. So a customer master key will be an encryption key dedicated to a particular customer, again, a BU, an application, a project. And when we have to store this key, we obviously cannot store it in clear text, so we will wrap it with the domain key and store it in S3. So on the previous schema, this EKT storage is the S3 bucket where we store the encrypted versions of the customer master key. And the customer master key, in turn, is wrapping and protecting instance secrets. So instance secrets are the actual secrets that will be used by Lux or BitLocker to encrypt your data. There is another view here when we can see kind of where those different keys are living in clear text or in their protected forms. So we can see the domain key only exists in the permanent memory of the HSMs. We can see the customer master key only exists in clear text in the HSM, but it's stored in this encrypted version in S3. And for the instance secret, we can see that the instance secret is stored in its encrypted version by the customer instance. We will come to that in a minute. And it lives in clear text in the memory of the instance. It's obviously necessary because else the instance wouldn't be able to do its job. And it also lives shortly in clear text in the HSM memory because it's the HSM that generates this secret simply. And for the EBS or instance storage that is protected, this storage will be split in two partitions, a little tiny partition of maybe 10 megs, I don't remember exactly, that will store the encrypted instance secret, and the data partition that will store your data and that will be protected by this instance secret. So that's the hierarchy. So this instance secret cannot be read by the instance, by the customer instance. It's just impossible. Why? Because it's encrypted with the customer master key, and the customer master key can only exist in clear text in the HSM. Therefore, in order to decrypt the encrypted instance secret, you must ask sovereign keys and the hardware security modules of sovereign keys to decrypt it for you. So when a customer instance is starting, it will have to communicate with sovereign keys and ask sovereign keys to decrypt its secrets. So it means that there is interactions, and it means that there is some things we should say about it. There is three main points that we want to ensure when it comes to communicating between the customer instance and the sovereign keys instance, or rather the HSMs of sovereign keys. Authentication, we want to verify that the customer instance is indeed who it pretends to be. Authorization, we want to verify that the secrets the instance asks for is indeed its own secrets. And we also want to transmit the secret in a form that will prevent others to intercept it. We only want the customer instance to be able to read it, but not everybody on the way, okay? So authentication is performed with this IAM role that we saw earlier on the schema. The principle is quite simple. The instance will send a request, and it will essentially tell, I have an encrypted secret. I am I-1234, and please, sovereign key, can you decrypt my secret? And the authentication part will be performed by the API gateway, by the Lambda, the custom authorizer. And it will simply verify, knowing the source VPC and the source IP address, it will verify by assuming the role here that the instance ID, the two instance ID, the instance ID is indeed related to the IP in the VPC. And if it's the case, we will consider that we are indeed talking with the I-1234 instance. So that's the way we authenticate things. Of course, that's not the classical way to go when it comes to authentication, and I would be happy to discuss it with you on why we are doing things like that. Authorization. So authorization is okay. We know it's I-1234, and it asks for a secret. Is it its own secret, or is it trying to steal the secret of another instance? So there is no conventional authorization mechanism because the instance secrets, as they are distributed, So I'm talking about this thing, or this thing, it's the same thing. It's cryptographically linked with the instance ID. So when we try to decrypt the secret, when the HSM actually try to decrypt the secret, we have to provide the HSM with the instance ID. And if it's not the same instance ID as it was when the secret was generated, it will simply throw an error and tell I cannot decrypt that. So if you want details, you can look up AES 256-GCM for Galois counter mode, which is the encryption mode we use to perform this feat. And at last, the transmission. So we authenticated the instance. It is secret. So now we have to send to the instance the clear text version of its secret, but obviously we cannot send it in clear text over the wire. So what we do is when the instance do its request, it will, before doing the request, it will generate an ephemeral RSA key pair, and it will send the public key with this with its request. And after verifying everything, when the HSM decrypts the secret, it will wrap it with the public part of the RSA key and send the wrapped version. That's this little lock you see there. And because it's wrapped with the public RSA key, only the private key can unwrap the secret. And the private key has been generated for the occasion by the instance, so it should only be on the instance. And that's it. We have some sequence diagram that you can use to if you want to know more. There is a final diagram putting everything together for a decrypt call. It's quite similar for a generate secret call, but hey. So yeah, if you want to verify you understood everything I say, you can pause the video and look at this diagram and verify that everything match. And with that, we will start installing it and playing with it in the follow. All right, so we are back for the getting started, and we will go over the getting started quickly and start the installation. And I will start this little chronometer, that a stopwatch, I think in English it is, the little stopwatch that you see over my head. So on the prerequisites, if we suppose that you know AWS, okay? AWS, and especially the core services of AWS, should be known to you. EC2 VPCs should not be a discovery, okay? We also use some of the developer tools of AWS, but you don't actually need to have experience with them. It will work alone, basically. And also, we will use some classical DevOps tools, so you should be familiar with Bash, Git, curl, SSH. And you don't have to be familiar with it, but you should have OpenSSL at hand, as we will use it a lot when we will configure CloudHSM. On the cost topic, for this test, you can expect cost to be below $10. Probably it will be $5, $6. The reason is CloudHSM. CloudHSM is quite expensive, and one node will cost anywhere between $1.50 and $2.50 per hour, depending on the region you choose. And CloudHSM is quite expensive, so yeah, for 2 hours test, it will be maybe $4 of CloudHSM alone. So when you are finished with the test, just don't forget to shut down your nodes, because the wake up will be painful or expensive at least. And after that, we go on the installation. So I will start the stopwatch, and here we go. So installation. So to perform the installation, you have to have an AWS account. It's kind of obvious, and you have to choose a region. For this test, I will do it in Frankfurt, because I do whatever I want, and I heard that our German friends are kind of interested in sovereignty. So we will use Frankfurt, but we already tested the API, the setup in Paris, in Ireland, in London. So it should work everywhere where you can find CloudHSM, basically. So the commands that will follow assume that you don't change the name of the project when we deploy the CloudFormation stacks. So you can change it, obviously, if you want, but if you do, some of the commands will not work anymore. And you can use a Linux bash. If you are under Windows, you can use Windows bash subsystem. It's what I will be doing, so you will know it works. And you can use ZSH if you are under Mac OS. And there is some slight differences, but it's quite the same. And so first thing first, choose a region. I will use this command because I find it more to my taste. And we will use uCentral1, which is Frankfurt. Obviously, I will not show you my credentials, but you will be able to see that I already configured my terminal. So I have indeed my AWS CLI that is working. I'm connected to my account, and I'm connected as an administrator. I suggest you do the same. Technically, we could restrict rights, but we have to manipulate IAMs and services that are not quite standard, like CloudHSM. So I think admin is okay. Okay, so back to GitHub. So before jumping in the in each section, I will just tell you what it does. So we will have four main steps, main section. So in the first section, this is this one, we will create the pipeline, the CI/CD pipeline to deploy sovereign keys, and we will create a start infrastructure, which is the infrastructure I showed you earlier, but without every compute resource. So we will just have the VPC, subnets, and some free resources, which will allow us to perform the second section, which is installing CloudHSM without paying for compute resources that doesn't do anything. So maybe I will use this. So first section, the CI/CD and some skeleton of architecture for sovereign keys. Second section, adding a CloudHSM cluster. It will be one of the longer thing to do. Third section, once we have the CloudHSM cluster and some critical information, we will be able to finalize the API installation. which is updating things so that the security groups are okay, that IP addresses, certificates are okay. So that's why the initial deployment of sovereign keys is in two parts. It's because we cannot entirely deploy it before knowing the HSMs, and we cannot deploy the HSMs before having a VPC. So yeah, at this point, the API will be working, and we will have to configure the customer agent. So the customer agent is the little programs that runs on the customer instances, and that will allow to communicate with sovereign keys without having a headache. So it will prepare the volumes, ask for the secrets, decrypt, etc. And obviously, to do that, it has to know the URL of the private API and some other thing that we don't know right now because they don't exist. So once we finalize the API installation, we'll be able to retrieve the last information that will allow us to configure the customer agent and create a working package for the customer agent. After that, we will do the usage part where we play with the API, and at the end, we will destroy everything from scratch to scratch. So, initial key provisioning, we will clone the GitHub repo. We will use a template, a CloudFormation template that is provided by the repo to create our CI/CD. It will create a code commit repository, a code pipeline, and etc. It will take 5 minutes. After that, we will copy the content of the GitHub repository in the code commit repository, and we will commit. And that will trigger the deployment of this skeleton architecture with the VPCs and subnets, but without the compute instances. So let's go. Oh, and I will reset the counter because I feel it's not fair that I didn't start installing anything and it's already 6 minutes. So I will reset it, not before showing you the AWS console. So I'm in my AWS console in the same account. Beware to be in the good region. So I choose Frankfurt, and I just want to show you that I don't have anything in that account, so I'm not lying to you. It's really from scratch. There is no VPC in that region, so you know that I cannot have any load balancers, instance, etc. And there is no CloudFormation stack. So really, the account in this region, it's clear. So I will reset the counter, and this time we will go reset. It has stopped, so I will start it. Okay, awesome. So I will just copy commands and go in my terminal. So you can see I have nothing in my home. So here it's clear also. I will just clone the repository and go in the repository. I have some files, and you can see I have the pipeline template.yaml, which we will use to create the CloudFormation stack using the command in step 2. There we go. And in step 2, we have to input a value. We have to input the value of globally unique company identifier. Why? It's because this template and the following templates will create S3 buckets, and you may know that S3 bucket must have a unique name. So this value you are providing will prefix the buckets so that we can ensure they have a unique name. I will name this one GRO SK. GRO is my trigram, Jérémie Rodon, and SK for sovereign keys. Okay, let's go. So I can see there is a stack ID, so it's in UU Central 1, so everything is okay. If I go to the console, I should be able to refresh and see the stack. Here we go. So it's creating, it will take 5 minutes, and it's useless to show it to you. I will, of course, let the counter run, but I will not let the video run. So I will come back in when it's done. Okay, so step 3 was a wait command, and it returned. So that means that the stack should have finished. I will just refresh, and yep, it's create complete. We can see that from 17:25, it started at 17:20. So yeah, it's 5 minutes. So it has been created. We have now, you can go over the resource quickly. So we have an artifact bucket, we have a pipeline, we have a code commit repository. And if you go and see the pipeline, so you just have to search for code pipeline, you will see that the pipeline already ran and failed. It's completely expected, so don't panic. It's because the code commit repository is empty right now. It doesn't have even have a branch. So the checkout failed and the pipeline failed, but it's completely normal, so don't panic. And we will continue the installation steps. So that means cloning the code commit repository, copying the entire content of the sovereign key repository, and committing everything so that the sovereign key main stack will be created. And I will again cut the video because it's not really useful to watch that. Just yeah, I will just do it. So first, retrieve the code commit repo name and the clone URL. So I will do that in my terminal. And you can see there is an HTTPS URL and a SSH URL. You can clone the repository with whatever method you like. Personally, I like to use the HTTPS method. So that's the one proposed in step 5 that I will copy right now. I like this method because, as you can see, it allows us to use a credential helper that is, in fact, the AWS CLI, which means that as long as you have in your environment credentials, AWS credentials that have access to the repository, it will work. It will work, and yeah, I find it simpler. We have cloned an empty repository. I was telling you earlier, it's completely expected. So I will use step 6 and copy everything from let's show that. So yeah, I am at the parent folder of both repository, which is my home, and I copy everything in the sovereign keys repository in the CC sovereign keys repo. So CC like code commit. After that, I commit with a message, initial commit, and I push. So as soon as I have pushed, here we go, a new branch master is created on the code commit repo. And if we go to the console and we look at the pipeline, we will see it right now, automatically it's triggered. And this time the checkout will work, and it will go on the build phase, and after that on the deploy phase. And yeah, it will take maybe 10-15 minutes. And I will just cut the video for the time being. Of course, the stopwatch will continue running. Just a word. Currently, I'm using this method to create the pipeline, but we also, by the time this video is out, there should also be a method to create the pipeline directly from a GitHub repository. So that should allow you to clone the sovereign keys repository into your own account and yeah, and use create a pipeline that will use your repo. It will allow you to avoid copying things around. But the rest of the installation will be the same. So with that, I will leave you. I will wait. I will use my the commands at step 7, and I will cut the video, and I will come back when it's done. Okay, so the wait stack create complete returned, so it's okay. It took less than 10 minutes actually, I think. If we go over the console, we can see that a bunch, let me reduce that, a bunch of stacks were created. That's because the sovereign keys main stack create some nested stacks. So that's why you have multiple nested stacks. The pipeline, yeah, 10 minutes. 10 minutes. And now you have some resources. So we have 2 VPCs, the Sovereign Keys API VPC, and the test customer VPC, which was the dummy customer VPC on the schema. And if we go over the EC2 instances, right now we have only one. We should have only one. And this solo instance is the bastion. And it's good because the next step, if we go back to GitHub, the next step is to configure SSH on the bastion instance. So because we are going to configure some critical cryptographic things, we don't want to do everything with Session Manager. We will prefer to use SSH because it's easier to convince ourselves that we have a kind of end-to-end security. I personally don't know how Session Manager is really implemented. I'm more confident with SSH. So we will configure SSH on the bastion. It's not really a step that I listed initially when I presented all the steps because it's really quick, not really related with sovereign keys. We will do that quickly. So we will generate an RSC key pair. Of course, if you already have one, you are welcome to use your current key. The goal is just to use Session Manager to go to the bastion, add our key to the authorized key of EC2 user, and verify it's working correctly. So it will be really quick. Just a quick word, there is an optional step 6 where you can change the configuration of the stack so that you ask for adding this thing will configure the security group of the bastion to only allow SSH connection from a specific IP range. I will not do it because it will have time for not nothing, but I will not do it. But you can do it, especially if you are in a company in enterprise professional environment. Enterprise environment, you may want to put the public range, public IP range of your company in there. That way, the bastion will only be accessible if you are on the corporate network. If you don't do that, the bastion is accessible from anywhere on the internet as long as you have the authorized key or one of the authorized keys, because of course you can configure the bastion to accept multiple keys. It's just SSH stuff. So let's do it. I will go in my terminal and I will just copy paste the commands really quickly. So create a new key. I don't need any password, of course. Okay, so now I have a public key. I will copy that thing. I will go on the Bastion using the session manager. So connect. For those who, you should know about session manager, I will come as root and I will echo my key in the authorized key of EC2 user. And I can just exit the Bastion now. Session terminated. That's good. My terminal. And now I should be able to use the command on step 7. So the first one is using the CLI to retrieve the public IP of the Bastion based on the name of the instance. So we store that in that variable. This variable will be used a lot in the future, so try to keep everything in the same terminal. And after that, we SSH into the Bastion using EC2 user. And as my default RSA key is now authorized, there is no trouble connecting. You can see I'm on the Bastion, and it's working as expected. Great. So now we arrive to the complicated part of the installation, namely adding a CloudHSM cluster. So of course, you need to perform this step only if you wish to use a CloudHSM cluster. If you wish to use a Protexio NetHSM cluster, which are the HSM of Atos, you can follow the alternative too. Obviously, I think most of you will not have a Protexio HSMs near hand, so we will use CloudHSM. So I will comment the steps as we are going. First, we need to create a CloudHSM cluster. So if I go in the console, I will go to CloudHSM just so we are a graphical interface to follow what we are doing. I have some backups because I obviously performed tests before this video, and I don't have a cluster. So I will use the first command to create a new cluster. As soon as I create the cluster, it will create the security group of the cluster. And the way CloudHSM is intended to be used is that you should put any instance, EC2 instance or Lambda or anything that should communicate with your HSMs, you should put them inside the security group of the cluster. Of course, you can also modify the security group of the cluster so you can open connection from the outside, but we will do it this way. So after creating the cluster, we will extract the security group ID and add the security group on the Bastion, because the Bastion will be used to configure the cluster. So it will need to communicate with it, obviously. So let's go. Oh yeah, and note that this is, I think, the only instance where the commands for ZSH are a little different. It's because this variable will contain multiple values, and bash will pass those values as multiple parameters to the CLI, but ZSH will try to be smart, and it will pass the content of the variable as a single parameter to the CLI, which will cause it to crash. So we have to ask ZSH with this little syntax to explicitly expand the content of the variable into multiple parameters. So if you are on Mac, just follow the ZSH, is what I'm trying to say. So go to my terminal and create a cluster. Awesome, it works. One thing that I will do, it's better if we don't stay inside the repository folder, we will create a CloudHSM folder, and we will perform the following steps inside this folder, because we will create a lot of keys, certificates, and we don't want to commit them or put them in the repository by mistake, because some of the files we will create are secrets. So yeah, secrets don't go in Git repositories. So now I have created the cluster. What I can do is to execute the second batch of command to extract the security group. First, I will describe it so you can see what the output of the command look like. So I have a cluster, it's create in progress. So, but you can see I already have the security group. I put the cluster in the private subnets of the sovereign keys API VPC. So it's quite logical. Private subnets, of course, you don't want your clusters to be exposed on the internet, so you don't use your public subnets. Everything is by default, so the backup retention policy and everything. I will use the next batch of command to extract the security group and add the bastion inside the security group. So that's this batch of command. So cluster security group, we extract it from the described clusters. So we can see it's the same value, that's fortunate. We retrieve the bastion ID, instance ID. We retrieve the current list of security groups of the bastion. We create a new variable with the current list plus the cluster security group, the CloudHSM cluster security group, and we modify the security group list of the instance. That's done with modify instance attribute. If we go in the console, we can see the cluster create in progress. We will let it be. And if we look at our bastion, we should be able to see that now it has two security groups. It's bastion security group and the CloudHSM cluster security group. Okay, that's expected. The initial creation should not be too long. Yeah, so now it's uninitialized, so we can go to the next steps. So step 2, when the cluster becomes uninitialized, that's what we saw. You can also saw it from the console, obviously. So if I perform a describe clusters, I will see that it's uninitialized. And that means that we can perform step 2. Step 2 is simply to create a node. So right now your cluster is empty. It's free also, so you don't pay at this point. You will only start to pay when you create an actual HSM inside your cluster, which is what I'm going to do. When you create the HSM, you choose an availability zone. I will choose the availability zone A because why not? It doesn't matter. You can choose any availability zone you like. Just change the command. And create in progress. This step will take 5 minutes, something like that. So I will go over the next steps so that you know what to expect, and if there is still time to wait, I will pause the video so that you don't just look at me waiting. So what will happen once we have the HSM node is it will expose a bunch of certificates. And that's something that it's interesting to explain. Sorry. So the step 3, which is optional, and I will not perform it because it's kind of tedious, allow you to verify that the HSM node you are creating is indeed an AWS CloudHSM v2 node. And it's interesting to see how it works. So what I will do is go to the AWS doc to explain to you how it's done. All right. So we are here on the verify HSM identity. And what will happen is as soon as the node we are creating is active, right now it's provisioning, but when it will be active, we will have 4 pieces of information that we can retrieve from the cluster. Right now, we can retrieve the AWS hardware certificate and the manufacturer hardware certificate. I can show you that in the terminal. If I describe the cluster, you will see that the output changed a little. Now I have an HSM because I'm creating it. It's creating progress. And I have 2 certificates, the AWS hardware certificate and the manufacturer hardware certificate. And when the creation process will be finished, we will also have the HSM certificate and the cluster certificate signing request. The goal here is the HSM, the node we are creating, will generate a public-private key pair. I don't remember if it's RSA or elliptic curve, but whatever. And what it will do is give us a certificate of this public key is just generated. And this certificate will be signed twice. It will be signed by the AWS hardware certification chain, which goes this certificate, which is in its turn certified by this certificate, the AWS root certificate. And this certificate, HSM certificate, is also signed by the manufacturer hardware certificate and the manufacturer root certificate. So it's signed by 2 certification paths. The AWS hardware certificate, as its name tells it, is the certificate of AWS. So it proves, because the HSM is capable of giving you a certificate signed by this AWS trust path, it proves that the HSM you are talking to is indeed installed by AWS. But it could be like a rogue employee trying to trick you, or maybe it's not it's not actually your HSM. Maybe it's I don't know, a simple EC2 instance. And that's why this certificate, the HSM certificate, is also certified by the manufacturer hardware certificate, which is the certificate of, I think it's Cavium, but the manufacturer of the HSMs. So when you do the verification, what you will do at some point is retrieve the root certificates, the 2 that were on the top of the schema, and you verify the chains. Basically, you verify that this HSM certificate is indeed signed by the AWS trust path and by the manufacturer trust path. Once you verify that, you know beyond any doubt that you are talking with an HSM that is installed by AWS, and this HSM is an hardware of, I think it's Cavium, but it's the intended normal hardware of CloudHSM v2. I say v2 because CloudHSM had a previous version, which was v1. So you will be able to verify that, and you will know that you are talking with a true CloudHSM HSM, and you will be able, and it's the last step on this page, to verify that the cluster certificate signing request contains the same public key as the certificate. So if you go to the end of this document page, the last command allow you to verify that the certificate and the certificate signing request are indeed related to the same key. And it's important because what we will do after the node is ready is to sign ourselves this certificate signing request, so that in the future, when we talk with the HSM, we don't have to perform all those verifications each time, which will be really, really boring and difficult. We will instead, after performing once the verification, we will instead sign the certificate, and we will just verify that the certificate the HSM presents us is indeed the one we signed. So yeah, that's the principle. I think there is a good chance that the HSM is ready now, so we'll be able to continue. Yes, it is indeed. So you can see the state is active, and you can also see that certificates now has 4 certificates, the cluster, rather 4 and 3, the cluster certificate signing request, the HSM certificate, and the 2 hardware certificates that were already there. So we will not perform step 3, but definitely you should do it if you are interested in those things. Instead, we will go in step 4. So step 4, we will take the cluster certificate signing request. We will just extract this value. We don't need the rest because we don't want to perform the verifications. We will extract the certificate signing request. We will create a private self-sign certification authority. So we'll start by creating a key. After that, we will create the self-sign certificate, which any root authority will have. And we will use this authority, this newly created authority, to sign the cluster certificate signing request and create the cluster certificate. Once the cluster certificate is created, we will initialize the cluster. Initializing the cluster means giving it its certificate and the root certificate we just created. So we will call this CLI with the 2 files we just created. So let's do that. As I said, put yourself in a dedicated folder for those steps, because we will create some private information. So first, retrieve the certificate signing request. All right. I'm just verifying that it's not 0, because if you perform this step too early, the certificate is not yet in the list and you will just retrieve nothing. So verify that you indeed retrieved something. We'll create the key. Oh, I just jumped over a command. Here we go. Create the key. It asks for a passphrase. You can put whatever you want. Obviously, if it's for production purposes, choose a true passphrase. We will sign the certificate. I jumped over. My commands are not aligned. So we will create the certificate. We input the same passphrase. It's a certificate, so we have to specify a distinguishing name. You can fill the value. I will just stay with the default value. I will just change the common name, and I will call that CloudHSM CA. Okay, so at this stage, I have a private key for my customer CA, and I have a certificate for my customer CA. I can now sign the cluster CSR. So I'm using OpenSSL once again to sign the CSR using the customer CA certificate with the private key which is there, and it will output the certificate. Obviously, I need the private key to sign, so I have to enter the passphrase again. And as you can see, I have now my CloudHSM certificate. And I can perform the last initialization step, which is calling the CLI and giving CloudHSM, the service CloudHSM, the two certificates I just created. It will verify that indeed I gave it a certificate signed by the trust certification authority I created. And it should take maybe, I don't know, 2 minutes. It's not that long. We can move forward in the meantime. So step 4 yields the customer CA.crt, and this certificate, that is the certification authority certificate, will be needed by all the CloudHSM clients to connect to the cluster, because this certificate allows the client to verify that the cluster is presenting a valid certificate, the one we just gave it. So as I want to configure my cluster, I want to configure the bastion to be able to connect to the cluster. And therefore, the bastion needs to know this certificate. So I will copy this certificate in the bastion. So I will do that with the command is in step 5, which is just a secure copy. Awesome. And I will go to the bastion and I will start configuring it. So that's step 7. Steps, I will just go over the steps because now it's initializing, so we have a little spare time. We will go on the bastion, we will retrieve the IP of the HSM node, the only node of the cluster right now. We will use the configure binary of CloudHSM, which is already installed on the bastion, by the way. You don't have to do anything. We will configure this IP, and we will move the customer certificate authority certificate in the expected directory. After that, we will use what we call effectively CMU, so the CloudHSM management util, and we will use it to really activate the cluster. So initially, the cluster will have a single crypto officer. So for an HSM, it's an administrator. And this single crypto officer obviously have a default password, which is password, and we have to change it. So the first step will be to change this password with a new password that we will choose. Of course, I will choose a password, not really a secure password, but you should choose a secure password for this step, because the crypto officer holds every power over an HSM, and it can reset the password of every other users. Therefore, it can access all the keys, use the keys, remove the keys. So it's quite critical. It's an administrator, okay? And so we will do that, and this pre-crypto officer admin will become the crypto officer admin. After that, we will use this crypto officer admin to create a new user, which will be a CU, so it's crypto user. And a crypto user is, it will be the user used by sovereign keys to interact with the cluster, create keys, perform cryptographic operations, etc., etc. So the password, once again, I will choose a not so secure password, but you should choose a secure password for this user, because this password will allow, if somebody knows this password and have access to your cluster, it will be able to manipulate the keys, decrypt secrets. It's kind of a catastrophic failure if you lose this password. And I will explain the rest once we perform that. I think the cluster has been initialized. Let's verify. So as usual, I will call, if I can find it, the describe cluster. And we can see that it is initialized. So we can proceed with the next steps. So I will go on the bastion. Okay, I should be able to find, yeah, I have my customer CA certificate that I just copied earlier. And I will perform the steps command of steps 7. So retrieve the HSM IP, configure the CloudHSM binary. So it creates this configuration, move the certificate. That's step 7. So I can go to step 8. So step 8 begins with launching the CMU, the CloudHSM management util. Okay, we can see it's working as expected. We can see the end-to-end encryption is enabled. It cannot work. At least you cannot have the end-to-end encryption enabled if you messed your certificate. So the fact that I have E2E enabled means that the customer CA is the right one, that I gave the right certificate to the cluster, and everything is okay up to this point. For step 8, don't execute those commands at one time, okay? Do not. The CLI, the CMU is not really a user-friendly CLI, and it will not work well because we cannot automate this part because there is interactive stuff going on, and we cannot make it non-interactive. It's really painful, but it's like that. So I will copy the command one by one. First, list users. So we can see the pre-crypto officer, and we can see a user that AWS is using to perform backups and extract the logs. So it has the audit role. So it cannot do any cryptographic operation, but it performs useful stuff to extract the logs and perform backups. So I will log in as the pre-crypto officer using the admin password. Okay, it's a success. I will change the password using a very, very secure password that we all know. It's a critical operation. It should be done on all nodes. I have only one node, so it's okay. Okay, success. That's good. So I can log out. And I can list users once again. And we can see that my pre-CO is now the CO. And at this point, the cluster is activated. So I can start playing with it and using it. So I will not exit the CMU. I will log in again. So I'm on step 9 of the GitHub right now. I will use my very secure password. Success. I will create my crypto user, sovereign key user, again using a very secure password, the same. Again, it is a critical operation. Yes, okay. Success on server 0. There is only one server, so that means success. I can log out from the crypto officer, and I can again list users, and this time we can see that there is my CU that's there. And that's it for the configuration. Now we have our user on CloudHSM, and we don't have it's quit actually. We don't have to come back to this CLI again. So I will quit, let it quit gracefully. We never know. And we can exit the bastion. And we can go back to GitHub. So there is another optional step there that is creating a second HSM in the cluster. Of course, if you are going to production with that, it's better if you have two HSMs in your cluster because only one means it can fail. Probably you will not lose secrets because there is backups going on, but it's still better to have two. Of course, for my test, I don't want to pay too much, so I will stay on one node, and I will not perform the step 11. And step 12 it's optional in the AWS documentation, but it's mandatory for sovereign keys because sovereign keys was created with security in mind. That's better for a cryptographic system, and sovereign keys expect to use a client certificate and a client key. So to perform the mutual authentication in TLS, so usually you only authenticate the server with the server certificate, which we already created earlier. But for sovereign keys, we also want to the client, so the sovereign keys API, to authenticate with a certificate of its own. So we will create this certificate. It's what we do in step 12. You can see it's quite similar to when we created the customer CA. We will create a key, but this time we will create a certificate signing request, and we will sign this certificate using the customer CA. It's really important that it is the same customer CA that we use to sign the cluster, the CloudHSM cluster certificate signing request. It have to be the same, else it will not work. Also, note that you must have a different DN for this certificate, so you should use a different common name. Of course, you could change anything else in the DN, but yeah. So let's do that. So I'm back on my computer. So I will create a new key. Note that I'm still in the CloudHSM repository. That's good. I will create my CSR. It asks me to enter some things. I will just change the command name. I will type in SK. I don't want a password. And that's it. My CSR is created. So right now you can see I have a CSR. And last step, sign the CSR using the customer CA. So here we go. Of course, it will ask me the passphrase for the key, because in order to sign, you have to know the private key. And that's it. And now I have my SSL-client.crt, which I just created. Okay, awesome. Back to GitHub. At this point, you should have 5 information with you. And if it's not the case, you should go back and find where you missed something. From step 1, creating the cluster, you should have the cluster security group ID. From step 4, creating the root certification authority, you should have the customer CA.crt. From step 12, what we just performed, you should have the SSL client CRT and the SSL client key. The key is obviously a secret, so treat it as a secret. And finally, you should have the PIN. It's the first time we evoke a PIN. For CloudHSM, PIN is a very generic term in the HSM world. But for CloudHSM, the PIN is the concatenation of the login and the password separated by a column. So I name my user SK user, and I use the password password1. Therefore, my PIN is this value. Okay. So note that somewhere. It's a secret, of course. So don't note it on your like on your desktop, or I don't know. So you should have those 5 information. It's not the case. Again, go back and find what you miss. The steps where you should have generated those values are referenced. So I have everything, so I will continue. I will continue on to the steps. So the 2 certificates, the customer CA and SSL client certificate, must be provided to the sovereign key instances. So in order to do that, we will put them inside the repository, and the CI process will copy those certificates into S3, and when the instances will start, they will be able to retrieve the certificates from S3. So the customer CA certificate is critical to be able to verify that the HSMs are indeed the expected one. And the SSL client certificate is because, as I said, sovereign keys will use a certificate to authenticate itself to the HSM. So I will copy those two values. I will copy the customer ca.crt inside my code commit repository. So it's in sovereign instance, CloudHSM conf. Okay, and same thing for SSL client .crt. All right. So step 13 and 14 done. Step 15. We have to modify the main configuration.json. So this JSON file holds the values of the parameters of the sovereign key CloudFormation stack. And what we have to modify is we will have to add an additional security group for the sovereign keys API instances. And we will give them the security group of the CloudHSM cluster, so that the sovereign keys API will be able to communicate with the HSM cluster. Second modification, we will change the value of toggle main resource creation to true. So this value controls whether we are creating a skeleton or the full system with the instances, load balancers, etc., etc. And we have to verify also that the HSM type is CloudHSM. Sovereign keys is currently compatible with 2 HSMs. Obviously, the configuration is not really the same, so we have to make sure that we have CloudHSM there. So I will do that. So I will exit my CloudHSM repository. I will go into the repository, the folder repository folder, whatever. And I can see there is a main configuration.json. I will edit that. Okay, so first thing first, I want that value to be true. HSM type is already CloudHSM, so I will just add my additional security group. And obviously, I want the real value, so I will find the real value. I will just quickly go in my console to copy the security group ID. I forgot to do it before. Okay, I have a comma at the end. Seems valid JSON, so I will save. And now it's step 16. You should really do a git status, and you should verify that you only modify that file, so the main configuration, we just modified it, and that the only additional files of the repository are the 2 certificates we copied just earlier. If you have any other new file, maybe you are like committing secrets, or I don't know, you should only have that. And if it's the case, you can just add everything, commit, and push. Obviously, new push in the repository means that the pipeline will be triggered again. So should be any second. I think it's already triggered, just the JavaScript, yeah. So it has been triggered, it's in the process of building. It will deploy the updated values for the parameters. And therefore, it will create the sovereign keys instances. it should take like maybe 10 minutes, 15 minutes. It's quite long because there is the creation of a private link between the network load balancer in front of the sovereign keys instance and the private API gateway that we use. So those two are communicating over a private link, and creating this private link is yeah, it takes like 5 to 10 minutes alone. So the update process is quite long. Therefore, I will keep the counter running, but I will pause the video and I will get back to you in a few minutes. All right, everyone. So I didn't trick you. It's not finished right now. We can see the CloudFormation stack CloudFormation is still busy, but we can also see that there is sovereign instances that have been created. So the long part I was talking about, the creation of the private link, is not performed yet, but we have sovereign instances, which means that we can actually go on with finalizing the API installation. So we will perform those steps right now, and they are quite simple. We will again go on the bastion by SSH. Do not use Session Manager for these steps because we will be giving our sovereign instances secrets, and we want to use SSH for that, not Session Manager. And once we are on the bastion, we will bounce to one of the sovereign instances, no matter which one. And we will give the instance the two secrets it needs. One, the client key, so the SSL-client key. So that is the private key corresponding to its client certificate, because of course, if you want to authenticate with a certificate, you will have at some point to know your private key. That's the entire point. So we have to give the instance that. And of course, they will need the PIN. So in order to connect to the HSM and perform cryptographic operations, they need to know the PIN. So let's do that. First, SSH and go on an instance. So SSH into the bastion and find an instance and connect to it. Of course, I agree. So, okay, I'm on an instance. You can notice I'm no longer on the bastion, which is 23 at the end, and I'm on another instance, a sovereign key instance. I used the mssh command, which is the command, the CLI provided by AWS to facilitate the use of EC2 instance connect. It is SSH, but using temporary keys. You can look it up if it interests you. So first, we will copy the key. It's important to do that in this order. First the key and then the PIN, because without the key, we are not able to connect to the HSM and try the PIN. So we have to replace the content of this placeholder by the actual private key. So I will do that in the background. Just give me a second there. Okay, I retrieve that, put it in place of the placeholder, copy the entire result, and go back to the terminal and show that to you. Okay, so obviously this private key is not really private because it's just a test. I will delete everything at the end. But in reality, you don't want to publish this private key in a YouTube video, okay? We can see that the command that actually gives the key did not return anything. It's expected, okay? So it should not return anything. We will see just after that when it returns something, it's a bad news. And we can see it's we give the key over HTTP because it's localhost, and this endpoint can only be called from the local loop. So there is no point encrypting the. I will give the pin, so I will copy the commands of step 4. And we can see that the pin was not accepted. And we can see that when curl returns something, it returns an error. It was not accepted simply because I did not change the value of the variable. So, of course, I did it on purpose. And remember, it's my user, so my crypto user on the HSM, colon, and my password. There we go. So if I re-invoke the curl, this time it doesn't return anything. It's normal. It means that it succeeded. If I try to call it again, I will have another error. It will tell me, hey, the pin is already present, so get out of there. And at this point, this instance on which I have replicated those information securely with its peers. So there is three sovereign key instances in the cluster, and all of them have the information, so all of them are able to perform work. And at this point, because the instances no secrets, I will not be able to connect to SSH. So if I try my MSSH again, the connection is refused, not because I have some problem, but just because the SSH daemon, the SSH daemon has been shut down on all the instances from the point they know secret. That's because those secrets should not be able to be extracted easily. So we don't want a human operator to just connect in the instance and extract secrets. And the logs of the API are exported to CloudWatch, so you don't really need to go to the instance while they are working. So that's why SSH is closed. Of course, it's a behavior you can change if you want. There is some options for that, but by default, that is it's like that. So if I go back to GitHub, I perform step 4, so I can exit the bastion, and it's okay. Right now, I have sovereign keys backend, so sovereign keys API instances that are working, and I will be able to go on the final installation step. So configuring the customer agent. So I will have to retrieve the private API gateway URL. And I will have also to retrieve the public signing key of sovereign keys. So I will just explain 2 seconds what it is. Sovereign keys, when it emits audit logs, or when it answers a generate secret call or a decrypt secret call, we already saw that there is encryption going on and so on. But it will also actually sign everything it sends so that the caller can verify that it's indeed sovereign keys that answers. And so the sovereign key agent, when it asks for a secret or asks for decryption of a secret, it will verify that the results it gets indeed comes from sovereign keys. And to do that, it will simply verify a signature. And to be able to verify this signature, it needs to know a public key corresponding to the private key that signs the thing. That public-private key pair cannot be known beforehand because sovereign keys just created them as soon as I gave the password, the pin for the HSM, the instances began to work with it. And one of the first things they do is create for themselves their signing key, which will stay the same afterward. But it's important that this signing key, the private key of this key pair, always stay on the HSM. We don't want it to exist anywhere else. That's this way you can know that it's sovereign key that signs things, because the key is in the HSM. And in fact, it's not even sovereign keys API that sign. It's really the HSM. So it gives you really strong proof that the information, the blobs that you received indeed came from the HSMs and have not been manipulated. To perform those steps, we need to wait for the complete deployment of the complete update of the CloudFormation stack. So I will verify it is finished. It is not. We need to wait because we need the VPC link. And the VPC link, I see the VPC link has been created. Yeah, indeed, it's in the process of finishing the update. So we can go on. As long as this link exists, it's okay. So back to GitHub. So again, go to the bastion, retrieve the private API gateway URL. So we will do that by describing the stack simply, and retrieve the signing key. So to do that, we will use the URL to call a specific endpoint, and this endpoint will just give us the public key. We have to trust this time that it is the good one. There is ways to verify it's a good one. And once we have done that, I will come back to GitHub. So here we go. In my terminal, go to the bastion, and first the private API URL. So I will call CloudFormation, and we can see that my private API gateway URL is that. I don't think it is possible to change it, at least some times ago when I was younger. It was not possible to change the private URL of a private API gateway. You can do that for a public API gateway, of course, but not for a private one. That's why it cannot be known before creating the gateway. And we will retrieve the public key. So I use this URL. I call with curl this endpoint, this public signing key endpoint, and I extract the right path in the result. It's a JSON result. And long story short, I'm creating this file, which is the public key, the public signing key of sovereign keys. In the follow-up on GitHub, I have to exit the bastion. Step 5 is to copy this little PEM file I just created locally, because the goal of the follow-up is to configure the agent. So we will go in the repo and we will change 2 values, so that next time we commit, and it will be the last time we do that, the code build container that creates the agent package will be able to create it with the right configuration. Until now, it was creating a package using dummy values that didn't mean anything. And after I do that, it will be able to create the real package, working package. So let's go. So step 7 and step 6. So step 6 is copying. So I will move it actually, because I'm already in the sovereign key repository. and I will move it in the path given to me, which is agent Linux sources sovereign. etc sovereign keys, and there we go. And I have to change the URL, so I will copy this value, and I will vim the agent Linux sources etc sovereign keys API url.txt txt, I think. I'm French, by the way, for those who didn't catch that. Okay, I remove the placeholder value, I save, and that's it. So step 8, add, commit, push, and the pipeline will be for the last time triggered, for the last time for this video, and it will create the agent. You have an optional step in GitHub, which is not really important. If you want, you can retrieve the RPM, and you have the 2 commands needed to download the RPM if you want to, I don't know, install it locally or whatever. And we can start with the usage part, because we are already at 1 hour and 25 minutes in our installation. So I only have 35 minutes remaining. And so usage. While the agent packaging is recreated, we can do a first thing. So we will use the test instance. So that is the instance is in the customer, the dummy customer VPC. We will connect to this instance using Session Manager. There is no point using SSH. Of course, if you want to use SSH, you can configure the instance and use SSH. It's up to you. I will use Session Manager. And we can validate that the API is working, okay? And I will show you all. How. Obviously, you can also read the GitHub, but I will show you how. So let's go on the instances, refresh this page, find the test instances. So this is this one, and connect to it using Session Manager. Okay, so I am going to be EC2 user, and if I look in the home of EC2 user, I can see 2 scripts. There is one script called functional testing.sh and install skagent.sh. Install skagent will be for later, but there is a functional testing script. And let's see what it does. So first, I will retrieve my API URL using the same describe stack I have done earlier in the Bastion. Remember, for now, we don't have a working agent. And I will call this script giving it the URL. Let's see. And it starts doing a bunch of things. And great news, the test succeed. So test succeed at the end of the script, this script, means beyond any doubt that sovereign keys is performing as expected. Okay? Let me just tell you what this script is doing. First, it calls the public signing key endpoint to retrieve the public signing key of sovereign keys. Again, there is no working configuration. Right now, the agent is in the process of being repackaged. So this script is completely independent of that. It retrieves its information itself. So it will retrieve the public signing key. Then it will call, or rather perform the actions to generate a new secret. That is creating a new ephemeral RSA key pair. Remember that when sovereign keys transmits a secret to an instance, it will transmit it in 2 forms. One, I will just go back quickly on the GitHub to explain that. One form is the secret encrypted by the customer master key. And another form is the secret wrapped so that the instance can read it. And we saw in this little section that to do that, the instance will create an RSA key pair, and when it asks for a new secret, or when it asks to decrypt an existing secret, it will give its public key to sovereign keys so that sovereign keys can wrap the result with the public key, and so that this customer instance, knowing the private key, is only one that can decrypt the result. So if we come back to this console, that's why we generate an RSA key pair, and we call the appropriate endpoint, stuff going on. We verify signatures of the results. We store the secrets. We convert the secret. We will get back to that in like 10 minutes. And finally, we decrypt the secret. So we once again call sovereign keys, once again generate an ephemeral RSA key pair. And at the end, we simply verify that the V1, so the secret we retrieved when we asked for a new secret, and the V2, the secret we retrieved when we asked to decrypt the secret, are the same. And the sequence of operation is done in a manner that it's only possible that it succeeds if the API is working as expected. So it can fail and the API is not working as expected, or it can fail and the API is working as expected, but you have another kind of problem, like a network problem, or I don't know. But it cannot succeed while the API is not working correctly. Okay, so this functional test is really complete, and it performs a complete coverage of all the features of sovereign keys. And if one of these features is not working as expected, it will fail. So it's a good test to do before giving your data to sovereign keys. If you want to know more, you can read the script. It's fairly well documented, of course, without syntactical coloration. It's a little tedious to read, but yeah, you can explore the script and you will be able to see the internal mechanics of sovereign keys client side, because essentially what the script does is the same thing that the agent does. Speaking of the agent, I believe it should have been, yep. So it has been repackaged 4 minutes ago. So we can go to the rest. So back to GitHub. So we performed this functional testing, and we can now install the sovereign keys agent. It's quite easy. We will use the script and we will verify the installation was successful by calling one of the CLI it should give us. Back to my session manager session and install SK agent. It doesn't return anything, but at the same time, it's a quite simple script. It will retrieve from S3, it will retrieve the RPM package, install it with a sudo, and remove the package. So not really difficult. And it gave us some sk- commands. So those are all the commands for sovereign keys. And we will call the check public key. The check public key do something very simple. It verifies that the local version of the key, so which is the one you have in your in the etc directory after installing the agent, it verifies that the local version and the remote version are identical. So they should always be identical, because sovereign keys will not change its signing key anytime soon. And if it does, it will you will distribute a new version of the agent, obviously. And And it tells us also that the installation was successful. So what's after that? After that, there is the other commands. So I will leave you to read that on your own, and I will just execute the commands and comment them as I go, starting in the same order of than GitHub. So I will go back on the console. Yeah, here we go. So I have on this instance, I have an additional volume. Okay, I can also show that with an LSBL key. And I can see that I have a little additional volume of 5 gig. And we will use this volume as if it was our data volume, and we will protect it with sovereign keys. So the first thing you want to do when you want to do that is to use the sk prep device command on dev SDF. I will do that. You have to invoke it as root, so either broot or use sudo. And it does a bunch of things, a little different from what you see in GitHub, because sovereign keys is evolving. And now we have also the ephemeral AWS public key that is displayed. Awesome. But it does some stuff. And in fact, what it does is preparing the volume so that it is actually in this form. So with the two partitions, one to hold the secret and one encrypted with Lux, because we are under Linux right now. So that is what sk prep dev is doing. If we continue with our demonstration, once we have prepared the volume, we can mount it. So yeah, I use the sk mount command, and I will tell I want to mount dev SDF on MNT data. And it tells me you must be root, so I have to do a sudo. And it will ask sovereign keys to decrypt the secret and initialize the volume. And now I have, if I tap just mount, which is a regular mount command, I can see I have something mounted on on MNT data. And if I do LSBL key, I can see that it's a crypt volume. Of course, you may not want to perform the SK mount yourself. So what you can do is sk umount for starters, so to unmount things. So I will unmount MNT data, so it will close the crypto mappers and unmount everything. And when you do the sk prep device, you can also tell it with a little switch that you want to automount the result on MNT data. If I do that, it will tell me that I have already data on the volumes, and probably I don't want to erase them. But if I'm sure I really want to erase everything, I can use the switch. So I will do that. If I am able to copy things correctly. There we go. And it will do essentially the same thing that I had last time, but this time it will automatically mount the volumes. So we should be able to see a little message related to that. Yeah, mounting the encrypted data volume. So I have my data volume that is mounted right now. And yeah, if you want to know more about the commands, each of them have an help. Oh, that's actually a mistake. But each of them have a help. So you can see what's going on and what you can do, what you cannot do. Obviously, the prep dev also have a help. And I will go ahead and create some super critical data in my MNT data. So here we go. So I have no super critical data in my MNT data. And I will reboot the instance to show you that there is some automatic mount going on. So the reboot should take only 15 seconds because EC2 instances are quite quick to reboot. So I will refresh that. Okay, not that quick, apparently. Still not that quick. Yeah, here we go. I will come back as an EC2 user. Uptime, I can see that it just rebooted right now. And I can see that my volume is mounted. And obviously, I can read my data. And here they go. So that's one thing. Another thing is maybe this instance will die one day. And in that case, I want to be able to restore it. So we'll do a short demonstration of that using the restoring a snapshot or an instance part of the GitHub. So in this part, what we do is first we will create an AMI of our test instance, the one we were just using. We can also snapshot volumes and it works, but it's just easier to create an AMI of the instance and restore it. So I will create the AMI, and after that we will wait for the AMI to become available. So I'm going on my terminal. I'm using the command of step 1. So step 1 is extracting the instance ID of our customer test instance. And after that, it calls the create image API to create an AMI from this instance. So when you create an AMI from an instance, it will simply snapshot all the volumes of the instance. And after that, it will create an AMI from those snapshots. So it should take maybe 2 to 3 minutes. We'll do a short pause, and I will be back once the AMI is ready. And my wait command returned, so that means that the AMI has been created. If I go in the console on the AMI page, I can see that indeed I have a new AMI available. And I will go ahead and create a new instance from this image. So this instance will be called customer test instance restored. So we will simulate the loss of our previous test instance. So I will copy that and I passed it. So this command sequence will just find the subnet ID. The subnet ID is, I think it's the subnet is in availability zone B, but whatever. And it will create an instance using the image, the AMI we just created. And we will go on this instance using system session manager. So let's go. We can see, so we can, the AWS console is a nightmare sometimes. We can see the restored instance. I will connect to it. I will go directly as root because I'm tired of typing sudo every time. And if I do an lsbl key, I can see that I have my 5 gig volume, but it's not mounted. And maybe it's because the SK mount was not performed. So I will invoke manually the auto mount. And we can see that it knows that it should mount something on MNT data. but when it asked sovereign keys to decrypt the secret, it failed. Don't panic, it's completely normal. It's normal because remember that this secret was generated from this instance. And this instance is high 00 EC something. And when our new instance asks to decrypt the secret, it's authenticated and it works. But when sovereign keys try to actually decrypt the secret, it sees that the secret is not owned by the instance, and so it failed. So it's what I explained to you at the beginning of the video when I was explaining the authorization part. The secret is cryptographically linked with the instance ID. So that's why it doesn't work. If we want it to work, and let me go back to GitHub quickly, we have to explicitly ask to transfer the ownership of the secret. It's not really a transfer of ownership because it will not really deactivate the previous version, but it will give us a secret that is usable for a new instance. So it's the sk takeown command, and to call that, we need to know the ID of the previous instance. You shouldn't have any problem with that because, for example, if you look at the AMI, it should contain the name of the instance it was created from. So if you look at the name, there is the instance ID in it. And I think the description of the snapshots should be quite descriptive as well. If you look at the description of the snapshot, you can see create image, and you have again the instance ID. Of course, you could use the audit log, and we will see the audit log just after that. I will go ahead and copy the ID. Oh, sorry, I'm not on the console. I forgot to. So I was showing the description of the snapshot, and I was showing the fact that the AMI also have the ID. So take on, I give the ID of the old instance, and I give the volume. It will call sovereign keys and will ask for the conversion. The conversion will be done. And the point is that now I can invoke the automount and it will perform as expected, just like a shard. And our volume is now mounted. So if I do an lsbl key, I can see it's mounted on MNT data, it's expected. And I can cut the content. And I have my secret, and of course I have the content of my secret. I didn't lose any data, and I only needed to go with sovereign keys to retrieve it. And that's it for the demonstration. And that brings a point, which is, okay, but it means that any instance can take home the secret of any other. And yes, it's necessary because if we wanted to invent some mechanism that would necessitate the original instance to perform the operation, you would be blocked or quite yeah, it would be bad, because if you lose this original instance, that would mean you lose the data, and you don't want that. So the take-home can be done by any instance of the same VPC. I simplify a little, but essentially that's it. And it's traced. And in fact, everything happening in sovereign key is traced. So to finish, we will go over the traceability. But because we are already at 8 minutes of the 2 hours marks, I will cheat a little, and I will cheat a little, and I will start destroying the resources before doing the audit. So this section describes you what you must do to destroy resources. If you want to just do a pause before tomorrow and you don't want to pay for resources, you can use those two sections. So the first one will instruct you to simply destroy the nodes of the cluster, of the HSM cluster. Do not destroy the cluster itself, and that way, when you recreate the node, it will be just as it never happened. The node will still have the keys, the configuration, certificate, PIN, etc. And after that, you just toggle the main resource creation to false, and it will destroy every instances. So you will not pay anything for the night. There is only the bastion that will stay, but you can shut down the bastion if you want. On the morrow, you just have to recreate an HSM, toggle the main resource creation to true again, and when the cluster is created, you have to redo the finalizing the API installation step. That is giving the secret key and the PIN to the sovereign keys API instances. Because, of course, if you destroy all the instances, they will forget everything. Because those configurations, those secrets that we gave them are not stored anywhere else. They are stored in the memory, is what I'm trying to say. So if you shut down the instance, no memory. And I want to destroy everything. So first I will remove every node of my cluster. I am not on the right page. Okay, so first I will destroy every node of my cluster. Okay, so if I am going to the console, on the CloudHSM console, I should be able to see that there is delete in progress. That's good. After that, I will toggle the resource creation to false, and that will take 5 minutes. So we will go over the 2 hours, but just a little. So that's okay, I guess. So toggle false. Destroy compute resources. Push. And before doing the rest, I will wait for this. I will go back to the I forgot to show the terminal, but yeah, I just edit the main configuration and push. We will go to the audit part because it's interesting. So everything the API, the sovereign key API does is audited and is sent to S3 bucket. So there is an S3 bucket for sovereign keys itself, which contains everything. And optionally, each customer can designate its own bucket to get the audit file. So you can see that in the console. If I go to S3, you will see all my buckets, obviously, but it's not really important. So this one is the main audit log bucket, and this one is the dummy customer audit log bucket. So if I go there, it's organized by VPC. There is only one, and we can see that there is a sequence of files. We can also see that this sequence is without any gap, and it's important. If there is any gap, it means that some logs have been deleted, which is obviously bad. It can, under certain circumstances, it can happen that there is a duplicate. So, for example, there could be 2.7. It can happen under normal condition, normal race condition. It's kind of unavoidable. But because of the way sovereign keys is constructed, you cannot have any gap. It's not possible. And how do you know those logs are really from sovereign keys, and how do you know they have not been modified? I will download one, so just so that we can see. We will not be able to see because I don't prepare the right window, but you can see example in GitHub of each call. So you can see that there are JSON files, quite detailed. You have the name of the call, the parameters, with even the public key that was used, who was the caller, at what time the call started, ended. You can see it takes less than a second for sovereign keys to process the request, and it's signed, and there is a signature, and this signature can be verified, and this is what we will do. There is other example. You can go over them if you want. Of course, if you are doing the test, you can download all your logs, and you will see. And if you want to validate the signature, what you need is obviously a log. And there is a utility provided in the repository that will allow you to divide this log in two. It will create two additional files. It will first extract the signature, so that is this part. And it will use the serialization protocol of sovereign keys, which is documented in the code, to create a serialized version of those information. And after that, you just have to verify that the signature corresponds to the serialized file, because the signature is done on the serialized version. So we will do that. We will do that for the log I just downloaded. So I will create a directory, verify sig. I will retrieve my my log I just downloaded. So it's 7, right? I need also the utility I was talking about, so I can find that in the repository. I can find it in utils, and you can see I have log file extraction.py. So I will take it, and now I can use this util. So I will invoke it on my JSON, and Python has not been found, probably because I need to specify the version. Here we go. And it created two additional files, the serialized version and the signature of the serialized version. If you are interested to see the serialized version, you can cut it, you can see it's just, yeah, whatever. And I will use the provided OpenSSL command to verify. Oh, let me, oops, there we go. Obviously, I need to change things a little. 07. Oh, yeah. And I just forgot one important step. I also need to retrieve the public signing key, because, of course, if you are verifying a signature, you do it using a public key. And I just forgot to copy that, so I will do it. You can recall we placed this this little file in agent, Linux, source, etc, sovereign keys, API, public key.pem. Okay, I copy it, and I invoke my OpenSSL, and this time it will tell verified OK. And if I try to modify my file, so for example, I will delete the number 6 in the sequence, and I want you to believe that this one is the number 6. If I once again reserialize and extract the signature, and I replay the verification, this time it's a failure. And it's a failure because the signature is not accurate, it's not the right one. And you cannot, nobody can regenerate the signature. Only sovereign keys can sign those files, because the key pair signing the files is a key pair that was created in the HSMs, and the private part never, ever leave the HSM. So only sovereign keys has access to this key. And that's it for the audit. So obviously, the files are not intended to be read by humans. All those processes should be automated in something like Elasticsearch or Splunk or whatever. You should also maybe correlate those logs with other logs to verify that everything is normal. I will just finish the destruction of the resources. So we can wrap up this from scratch to scratch tutorial. I was there. I need to remove the cluster security groups from the bastion. I will do that from the console. There is no point doing command. And I need to do that because else, when I delete the cluster, you can see everything is terminated or shutting down. When I delete the cluster, if the bastion still has the security group, the cluster will not delete the security group. If the security group is still there, then the CloudFormation will not be able to delete the VPC. And yeah, it's quite annoying, is what I'm trying to say. So, okay. Then remove the cluster itself. Okay, this time we provided a command, so let's just play it. Okay, delete in progress, that's expected. After that, we can empty all the S3 buckets. So those buckets, the audit buckets and the EKT bucket that contains the encrypted version of the customer master keys are quite critical. So they are configured with object lock, but by default, the object lock mode is compliant. You can change it in the parameters of the stack. You may have noticed that in the main configuration file. There is an object lock mode, and by default it's governance. So in governance mode, you can still delete things. So for a test, it's probably what you want. But in production, you probably want to put it in compliance mode so that nobody can delete the files in those buckets. And it's especially important for the EKT bucket, because losing a file in there means losing a customer master key. And losing the customer master key, if you look at the hierarchy, it means that every instance secret protected by this key will be lost as well, which means in turn that every data protected by this instance secret, or all the instance secret, will be lost as well. So you don't want to lose those keys. You don't want to lose them at all. It is a test, so I will empty those buckets. So I will go in S3. And so audit logs, customer audit logs, and EKT. So those 3 buckets, I will do them in order. I have to type in permanently delete, empty. Second one, permanently delete, empty. Third one, permanently delete, empty. Okay. What is the GitHub saying? Terminate the instance restored. Yes, indeed, because it's not part of any CloudFormation stack. CloudFormation will not do anything to this instance. So we need to shut it down manually. It's the only instance remaining saved for the bastion, but it's normal that the bastion is still there. Terminate. And at last, we can delete snapshots and delete the stacks. So I will do that, and I will be able to stop this stopwatch. So delete the AMI, delete the snapshots. And in CloudFormation, delete the stack. That is the main stack. No need to delete one by one the nested stacks. And I just have to wait for the deletion to complete. It may take, I don't know, 5 minutes. And once everything is deleted, it should be less than 5 minutes actually, because we already destroy the vast majority of the compute resources. So there is only like VPCs and empty buckets to destroy. So it should be quite quick. Whatever you do, don't be too hasty, don't be too quick, and don't never delete this stack before this stack is entirely deleted, because this stack is one of the resources of this stack is the role used by this stack to manage the resources. So if you delete this pipeline stack before deleting everything else, the main stack will fail, is what I want to say. So be patient. We are not at 2 minutes at this point. 2 minutes more will not kill us. So here we go. It will delete the VPC. Hopefully I didn't forget anything, and those VPC will be able to be deleted without any problem. I can sense I forgot something, because yeah, I think the cluster security group is still there. Yes, that's unfortunate. I guess I removed the cluster too quickly, while there was still instances with the security group. Anyway, so yeah, it will be deleted. Afterwards, I will delete this stack, and at this point, I will be returned to scratch. So I will just, yeah, okay, it's okay. Everything is disappearing right now, and yeah, I can delete this stack. And after that, it will be from scratch. I think I can stop the stopwatch right now. It's quite fair. I use some time to explain things, so we can say the challenge was okay. It's 2 hours, maybe a little more, maybe a little less. I am quite chatty, so that's why. Thank you for following this video. In the repository, you will find additional information if you want to contact us. So if you want to contact us for doing a POC, or if you want to contact me simply to discuss things, that's possible. And yeah, I would be happy to chat with you, and I will wish you a pleasant day or evening or whatever. And I hope this was helpful. And yeah, don't hesitate to comment, to give feedback, and have a nice day.